Alright, so what we're going to do is verify the following. Remember, when verifying, you can only manipulate one side of the equation. So if we are verifying the left, we have to leave the right as the cosine. So we're going to change all of this stuff on the left to sine and cosines. So cotangent is sine. Just kidding. Cotangent is cosine over sine all over cosecant, which is 1 over sine. And then what we need to do is get rid of the fraction and fraction, so we multiply both sides by sine theta over 1. And we'll notice that sine theta cancels in the bottom, sine theta cancels here, and we're left with cosine theta, which is what we were trying to verify, and we are done. Next, so here we're going to keep the simple side of cosine beta, and we're going to transform the other side. So we're going to look at 1 minus sine squared. I'm just going to write thetas instead of betas, all over cosine theta equals cosine theta. So 1 minus sine squared theta, well, that's a manipulation of the sine squared theta plus cosine squared theta equals 1. So what we did was subtract the sine squared from both sides. So when you do that, you get 1 minus sine squared. So what that means is we can replace the 1 minus sine squared in this problem with cosine squared. And then when you have something squared on top of something linear, you can subtract the exponents. So cosine squared theta over cosine theta becomes cosine theta. And once again, we are happy because we get cosine theta equals cosine theta. We have tan theta over secant theta equals sine. So we're going to change the complicated and make it simple. So the tangent of theta becomes sine theta over cosine theta. Secant of theta becomes 1 over cosine theta. We can't have a fraction and a fraction, so we flip it. Denominator cancels, the cosines cancel, and we get sine theta equals sine theta. Tan squared theta plus 1 is also a manipulation of our Pythagorean identities. So we're going to replace that with secant squared theta over secant theta. And again, 2 over 1 is the same as like x squared over x. You subtract your exponents. So we get secant theta equals secant theta. To solve, we're going to solve for the trigonometric function. So we have 2 sine x minus 1 equals 0. So we're going to solve for sine x. So we're going to add 1, divide by 2, and we get that the sine of x is equal to 1/2. We need to think back to our unit circle. Sine is positive in quadrants 1 and 2. And then what we're going to do is the sine of x equals 1/2 at 30 degrees. So at 30 degrees, that's also the same as pi 6. So x equals pi 6 in quadrant 1. And then we know 30 degrees is over here in quadrant 2 is the same as 150, or pi 5 pi over 6. In calc, we tend to use radians. In physics, you'll use degrees. So you just need to get good at both. We can see that graphically here. Now, when I answered for this problem here, I gave my answers in terms of a domain 0 to 2 pi. We know that this sine function technically is infinite. Its domain is all reals. So technically those answers repeat over and over and over again. So you can see on the graph, here it is at pi 6, here it is at 5 pi 6. But technically it occurs again at pi 6 plus 2 pi, at 5 pi 6 plus 2 pi. And the reason we're adding that 2 pi is because the circumference of the unit circle is 2 pi, because circumference is 2 pi r, but we know that the radius of the unit circle is 1. So on our unit circle, we had those 2 points at pi 6 and 5 pi 6. Well, what happens is as you travel around and around the unit circle, here's one trip. Well, on the second trip, we hit it again and again. And then as you continue around, traveling around and around and around that unit circle, you continue to hit it over and over again. So we account for those multiple hits by adding 2n pi to each answer, where the n represents the number of trips we make around the unit circle. We can also think of the solutions in terms of a quadratic. So 2 sine squared x minus sine x minus 1 is similar to saying 2a squared minus a minus 1. You're going to factor it so that you have the quantities 2a plus 1, a minus 1. But then instead of using the variable a, we're going to use sine. So that's like saying 2 sine plus 1 sine x minus 1 is equal to 0. And then in order to solve for x, we're going to set each factor equal to 0 using that zero product property. So you have 2 sine x plus 1 equals 0. Sine x minus 1 equals 0. So you get that the sine of x is 1 and that the sine of x is negative 1/2. And then we need to know our trig values at which that occur. So that occurs when x equals 11 pi 6 and 7 pi 6, because it's the opposite pi 6 values from before. So now sine is negative in 3 and 4, and sine is equal to 1 at pi halves. We can also do it where there's a multiplier on our angles. So we're going to once again isolate cosine. So we're going to add 1, divide by 2. And then it's kind of like the same as taking the inverse cosine of both sides. So the inverse cosine of 1/2 is pi thirds. So when you take the inverse cosine of the cosine, they cancel. So you get 3t equals pi thirds. It's also going to be, because all students take calc, in quadrant 4. So that's 5 pi thirds. But we haven't solved for t yet. We solved for 3t. So we have to divide both of those by 3. So t is equal to pi ninths and 5 pi ninths. But once again, there's no domain restriction. So what that means is this is cyclical again. So it's pi ninths plus 2 and pi thirds. and 5 pi ninths plus 2n pi thirds. The reason it's divided by 3 is because of the 3 in front of the t from up here. So we had 3t is equal to both of the unit circle values, and then those unit circle values are going to repeat in terms of thirds because it's now a much faster cycle. If you recall from last year, that is one of those transformations in which the cosine's period's been shrunk and it occurs more frequently.